Hello everyone. So we're talking about topic 2.2. It starts on page 9, so open your notes, follow along, and make sure you're filling them out as you go. I'm just filming this video right after the 2.1 video, so I'm still using my same awesome pen as last time. So what we have going on here is intramolecular forces and potential energy. So let's start off with this idea of intra, okay, versus intermolecular, okay? So imagine we have a water molecule. It's got polar covalent bonds holding this water molecule together. And the difference in electronegativity between the oxygen and the hydrogen is fairly different. So we definitely get a partially negative region of this molecule and a couple of partially positive regions of this molecule. Okay, so I have this molecule. The electrons are not evenly distributed throughout it. They definitely are spending more time with the oxygen and less time with the hydrogen. And then it wanders by another water molecule, which also has, I'm adding the lone pairs this time, I didn't put them on that one, but which also has this partially positive side and this partially negative side, okay? And we know that anytime there's positives and negatives around each other, that there's going to be an attraction between them. So this part of the molecule is going to be attracted to that part of the other molecule. So I'm going to do a dashed line to represent this, okay? When we have attractions between molecules, this is called an intermolecular force. But when we have attractions inside, within molecules, like that polar covalent bond holding those atoms together inside those molecules, that is an intramolecular force. So intra is within the molecule, or another way of thinking about it is what's holding the atoms together to make up this molecule, and inter is between these molecules. So here's the atoms that's making up this molecule. Intra is the force that's holding the atoms together to make up this molecule, intra. Inter is the attraction between these molecules. That's an intermolecular. So intra, inter. Way more on intermolecular forces later. Right now we're concentrating on intramolecular. Okay. I saw a lot of these graphs when I was looking at the practice problems. And so here's the idea. And in class, I'm gonna show you a simulation of this that does such a good job of explaining what's happening here. And I actually don't love this example. We're going to draw a new example, okay? So imagine that one of the two atoms involved is going to be right here, okay? And yes, it's got its positive protons in its nucleus, and it's got its negative electrons flying around. And I'm going to have another atom that's going to start way over here. And the first thing I want you to know is that they're fairly far apart from each other. So much so that there's not much interaction between them. There's not much attraction or repulsion between these atoms. That's why we get this like no interaction portion, okay? But what if through random motion one of these atoms becomes close enough to the other one that something happens? And what's happening is that the positive protons of this atom are attracted to the negative electrons of the other atom. That there is this, this dot represents like the center of this atom. below, and what we're seeing is that there is an attraction that this atom has for the other atom. And what is happening is the protons of this atom are attracted to the electrons of that atom, and that's what's pulling it towards it. Now, we should also note that this other atom has a nucleus as well that's positive, and those positive protons are repelling the protons of this one, but just not nearly as much as the attraction. Like, it's uneven right now. The attraction is greater than the repulsion. Okay? And so if I were to let go of this atom right here, well, then it would pull its way into the other one. Except we're going to get to this point here. Now, see how it says increasing attraction? That's this portion of the graph. This is our increasing attraction portion of the graph. And notice that our potential energy, the energy of these atoms, are decreasing. It means it's preferable, that this is a more stable arrangement for these atoms, that if I were to just let go of it, it would naturally want to end up right here because that's where the energy is the lowest. But why is energy the lowest there? Well, that's due to the fact that the attraction that this nucleus has for the electrons of the other atom are now equal to the repulsion that this nucleus has from the repulsion on that nucleus. These positive protons are now pushing away the protons there, and they equal each other out at this low point in energy. Okay? Another way of thinking about this is that's where these atoms are going to want to be in relative space to each other. This distance between the nuclei of this atom and this atom at that low point in energy, this is the bond length. Now, I will admit that where I am a little limited here is traditionally we see an overlap of the electron clouds at this point. That, like, when two atoms are bonded, we kind of get this thing going on. Not always, but commonly. And so then that distance between those nuclei, that would be our bond length. But a reminder, that's when the attraction that this nucleus has for the electrons of the other atom is equal to the repulsion that the nucleus of the other atom has on those protons there. Okay. I've already been talking through this, and so I'm not going to dive into too much here. But sorry, put a pin in this next thought. We have one more spot here. What if I force these atoms to be closer than they want to be? Like, what if I push this atom closer to the other atom? It doesn't want to be there, but what if I force that to happen? Okay. So what if I force this atom to be closer than it wants to be? I'm going to draw, sorry for the messy notes. I'm going to draw the forces of this one right up here. So this atom is way closer to the other atom than it wants to be. There is still an attraction between the nucleus of this atom and the electrons of the other, but look at how close those nuclei are. Those positive nuclei are way closer than they would ever want to be, and they're definitely repelling each other at a really large magnitude. And so if I were to let go of this atom right here, it would get like slingshotted away, and then it would come back, and then it would settle right into that happy spot again where the energy is the lowest. Okay. That's why you see increasing repulsion. It's the nuclei that are repelling each other, and that's what's increasing. Can we use Coulomb's law to describe everything that's going on here? Yes, absolutely. So do not forget that Q1 and Q2 represent the two charged things. So we could be talking about both nuclei, right? The nucleus of either one or both of these things, the two nuclei that are going to repel each other, or we could be talking about the electrons. So one could be the nucleus of one the nucleus of one atom and the electrons of the other atoms. That's also fine. So Coulomb's law can be used to explain both the attraction and the repulsion that's happening here. And r, as we know, is the distance between these charged things. And so if we have two oppositely charged things that are closer together, then there'll be a greater attraction between them. If we have oppositely charged things that are further away, then we have less attraction between them. And that's what we're going to notice with bond length and strength. So use Coulomb's law definitely to talk about the strength of these bonds, because what tends to happen is that bonds, shorter bonds, okay, there's my bond length, those tend to be stronger. Their attraction between them is greater, and so it takes more energy to pull them apart. And then longer bonds, there's that bond length, they tend to be weaker. They're further away from each other, so the attraction isn't as great, and so it's easier to pull them apart. All right, let's use this concept to answer this question here. So this figure shows two graphs of the electrostatic potential energy versus internuclear distance. Okay, it's the same graphs we were just looking at. One is for a pair of potassium and chloride ions. The other is a pair for potassium and fluorine ions. Which is which? So I don't know which line yet, but I know that one is potassium with fluorine, and I know that one is potassium with chlorine. Okay. Now let's draw a picture of this. Here's my two potassium atoms. They're the same size as each other. And now we're going to make a comparison between fluorine and chlorine. Fluorine and chlorine. Well, we know as we go down the group, the atomic radius gets bigger. So here's my fluorine, and then here's my chlorine. Okay. Now, due just to the size of these atoms, even if there is a little overlap here, the bond length is definitely going to be different, right? We're going to have a shorter bond length for the potassium and the fluorine, and we're going to have a longer bond length for the potassium and the chlorine. So where it dips down, that represents where it's perfectly where it wants to be, and the distance represents the bond length. So this is the bond length of this lower line here, and this is the bond length from here to here. That's the bond length for this upper line of this graph. So from that alone, I can choose this line to represent the potassium fluoride bonds, and then for this one, the potassium chloride bonds. Okay, great. Here's the other interesting thing. Remember that the y-axis is energy, and this is the lowest possible energy where they're the happiest, okay? In order to do the opposite of the graph that we talked about before, in order to go from here to here where they're completely separated. I grab this guy and I pull it away so there's no longer any interaction. This is how much energy would have to be added. I'd have to add this much energy to be able to pull those guys apart. This is the bond energy. So the bond energy for this potassium and fluorine is bigger than the bond energy for the potassium and the chlorine. And that makes sense according to Coulomb's law. It makes sense that the longer, the bigger bond would require less energy to pull it apart, and the smaller bond would require more energy to pull it apart. Critical thinking, where would the curve for Ki be located? All right, so here is our Kf, this is our KCl, and now we got a Ki thing that we have going on here. Well, what would that look like? Oh my goodness, iodine's all the way down here. So it is way bigger than both chlorine and fluorine. So like if there's our potassium, well then our iodine is huge, right? And so this would be the biggest bond length of all of the ones that we just barely looked at. So I would definitely need the bottom of the peak to be further to the right because I need the biggest bond length. And if the bond is so much bigger than the other ones, then it probably takes less energy to pull them apart. And so I would need that dip to not be as low. It would be higher, so somewhere up there. It doesn't really matter where you draw it, but it needs to be to the right of the other ones. And it's got to be more shallow than the other ones. All right, so this brings us to our concept of lattice energy. I'm going to grab one of these models. Okay, the first thing I'm going to do is kind of explain the opposite of what lattice energy is. I think it's easier to understand that. And then just recognizing that lattice energy is the opposite of this idea. So this is an ionic compound. It's made up of metals and nonmetals that are ions, and there's a great electrostatic attraction between these things. All right? Quiz, which one's the cation and which one's the anion? It's due to its size. Cations lose electrons, and so that makes them smaller. Anions gain electrons, that makes them bigger. And there's obviously an attraction here between these things, right? Now, what if I wanted to pull this whole thing apart, atom by atom or ion by ion? Well, it doesn't just naturally do that. I would have to add energy to be able to do this, to be able to pull all of these ions apart would require energy. I'd have to add energy to pull them apart. Another way of thinking about this is how much energy would it take for me to take this and slam it on the ground so that it all broke apart from each other, okay? That idea, how much energy it would take to pull this lattice, this crystal structure apart, is the opposite of what lattice energy is, okay? That we'd have to add energy to pull this apart. So then if we do the opposite of that, if we take these, like I did at the beginning, and I put them all together, well, energy must be released when these things come together. And it would be the exact equal amount of energy that would be lost to pull it apart. You can even hear this, like, when these things want to come together, energy is released, and for this model, we hear it as sound, okay? That's what lattice energy is. Lattice energy is how much energy is released when we go from these like free-floating ions to them forming a lattice energy, okay? So the energy released when ions form a lattice or an ionic compound when they form the structure. And this lattice energy is going to be equal in magnitude but opposite in sign. Equal in magnitude but opposite in sign to the energy required. Okay, equal in magnitude but opposite in sign to the energy required to break apart the lattice. All right, so that means for this particular example, if it took me 10 kilojoules of energy to pull all of these apart, then that'd be a positive 10, right? Because I had to add that energy to pull it apart. Then how much energy would be released when it comes back all together? That would be 10 kilojoules. But because it's energy that is released, not like added, but like lost, that's why it's a negative sign instead of a positive sign. So if it's energy that's lost or released, then we put a negative. But if it's energy added, then it would be a positive. So just a heads up, I mostly see lattice energies as negative for that reason, but on occasion I have seen a list of lattice energies that they listed as positive, and it's still just how much energy was released when the lattice was formed. So don't let that trip you up. Okay. Great. Now, there's two main things that affect how much energy it takes or is required to break apart two ions, okay? And Coulomb's law will give it away. So electrostatic force, Q1, Q2, which is the charges, and then R squared, which is the distance between these ions. All right. So when you're asked to compare lattice energy, I need you to know that the charge of these ions is way more important than the distance between these ions. That this part, its magnitude is so much bigger than that part of this equation here. Okay? So when you are comparing how much energy it takes to break apart this set of ions versus another set of ions, when we're comparing lattice energies, the first thing you should always check, so first should be the charges of the ions, okay? And then the idea here is the greater the charge, the larger the magnitude of the charge, the greater the lattice energy. So the greater the charge, the greater the lattice energy, or vice versa. All right, here's my example for you. If I was going to compare the lattice energy between NaCl and MgCl2, this lattice energy is so much bigger, not because there's two chlorines, but because sodium forms an ion with a +1 charge and chlorine forms an ion with a -1 charge. But magnesium, on the other hand, forms an ion with a 2+ charge, and chlorine is still that -1 charge. That greater charge means that this lattice energy is way more than that. Now look at our list here. There's the sodium chloride, and so 786 kilojoules per mole of sodium chloride is released when it's formed, but way more than that is released when magnesium chloride is formed. Okay? It took more energy to break this guy apart. than to break that one apart. Now, if we run into a situation where the charges are the same, then you should consider the distance, the radius of these atoms, okay? So the second thing you should consider is atomic radius. And so here's my example for this one. What if we're going to look at sodium chloride again, and this time we're going to compare it to lithium chloride. The charges are the same. We got sodium, which is a +1, chlorine, which is a -1, lithium, which is a +1, chlorine, that's a -1. But lithium is smaller than sodium, right? It gets bigger as you go down the group. So, due to this smaller radius, right, like let's draw a picture really quick. Here's our sodium and our chlorine. And here's our lithium and our chlorine. This bond length is bigger due to the bigger radii. This bond length is smaller due to the smaller radii. And we know when the distance between these charged things is smaller, then the attraction is greater. So for atomic radius, when the atomic radius increases, the lattice energy decreases, right? The larger the radius, the less energy it takes to break them apart, or the smaller the radius, the more energy it takes to break apart. So this one should have a larger lattice energy, and this one should have a smaller lattice energy. And let's see what we got here. Sodium chloride, it takes 786 kilojoules of energy to pull a mole of sodium chloride apart, but it takes more energy, 864 kilojoules, to pull apart a mole of lithium chloride. So that one had a greater lattice energy. Okay, and then we will look at page 11, just really the practice problems in class. Same with page 12. I really have already talked to you about this already, that when the bond length is smaller, then the bond is stronger, and when the bond length is bigger, then the bond strength is weaker. And so the last thing I want to talk to you about is bond order, or the number of bonds. So if we have a single bond, which happens between two fluorine atoms, that means that each fluorine atom is sharing, again, reluctantly sharing, but each fluorine atom is sharing one electron. This fluorine atom is attracted to its own electron plus one electron of the other fluorine, and then vice versa. That's a single bond. But if this happens for two pairs of electrons, that would be a double bond. And then for three pairs of electrons, this would be a triple bond. Okay? The greater the number of electrons, the greater the bond order and greater the strength. Like we would say that this has a bond order of 1, this has a bond order of 2, and this has a bond order of 3. And it requires more energy to break apart a triple bond. Okay, more energy to break apart a triple bond, and the least amount of energy to break apart a single bond. And also in general, not always, but in general, triple bonds tend to be shorter and single bonds tend to be longer. Okay, like we tend to get this like single bond and then double bond and then really short triple bonds. Okay. I know that this question, it doesn't work perfectly, but it does show up on your unit test, so let's make sure we talk about that one in class. And yeah, all right, lovely. I'll see you all in class.